not recognise this as a radio player, but believe me, this is the kind of reception you would often get with an older radio before we went digital. It's amazing how much of a difference it can make. For example, which direction the aerial is pointing. The radio waves are used for much more than just sending the radio signals. For me, for example, radio is very important because a lot of the information that we gain from stars comes from radio, as well as the light that we receive from them can be very important. For example, a tiny amount of the static that you hear sometimes on radio or TV stations, they're also broadcast by radio signals. And I know it's a little bit confusing, but it's part of the radio portion of the electromagnetic spectrum. A part of that static you sometimes get is from the planet Jupiter, for example. A part is from the Sun and from the other stars. And what's really amazing is that a tiny portion of it, really down in the microwave part, so almost into the microwave part of the electromagnetic spectrum, there is a tiny signal which is actually left over from the Big Bang, the creation of the universe. And that for me is mind-blowing. Every time we hear that static, we're actually receiving a little tiny bit of the original radiation. But it's been changed as the universe has expanded. More about that another day. However, today the electromagnetic spectrum, obviously radio waves, they also carry TV signals. We use them for all sorts of communication. X-rays, we use them to look inside the human body for medical reasons, much safer than cutting someone open sometimes. And wherever possible we will do that rather than invasive surgery. We also use it for security, for detecting hidden bombs or smuggled items when we're going through customs. But there are other parts of the electromagnetic spectrum as well. Now I can't give you a demonstration of gamma rays today, but they will crop up both when you look at space and also when you look at radiation, nuclear radiation. They're at the very high end of the electromagnetic spectrum, the most dangerous end, and we can make use of that very high energy in various different ways. We can use it to sterilise, kill the bacteria on surgical instruments or even food to stop it from going off, or to stop infection when we're performing surgery. We can also use it to actually kill cancer cells, but we have to be obviously very careful because high energy electromagnetic radiation, X-rays and gamma rays, can actually cause cancer. So we do need to be very careful. There are other parts of the electromagnetic spectrum as well. Microwave, for example. Now, I've got a microwave oven over here, and I happen to have a chocolate bar that I've cut in two. Now, I'm not going to share it with anybody. The reasoning behind this is to show you a simple practical with a microwave oven. What you do is use the microwave oven to cook for just a few seconds the chocolate. Now, microwaves, like all waves, can travel, and they can have peaks and dips where there's a lot of energy, and they have that 0 point in the middle where there's not a lot of energy. We should be able to, if we only cook this chocolate bar for a few seconds, we should be able to highlight where those particular hotspots are, where the energy is at its highest. And that's where the chocolate will melt first. So, only takes a few seconds. Just cooking some chocolate over there. And again, I'm looking for the hot spots where it will melt first, where the most energy on that wave is coming from. Well, I didn't have to wait long. The chocolate bar has melted, not everywhere all at once, but at two distinct points, here and here. Those are the hot points, the points where the waves have the most energy. If I measure the distance between those two hot points, that's half a wavelength. So that's about 6-7 centimeters. If I know the speed of microwaves, which is the same as the speed of light, so 300 million meters per second, I can work out the frequency of my microwave oven. And of course I can also enjoy the chocolate. But Microwaves are also very useful for other things. For example, our mobile phones. You might think, like the old days of radio transmitters, that's what we'd be using, but no. Mobile phones actually use microwave signals, and they can carry so much information for us. We also use other parts of the electromagnetic spectrum to carry information, apart from radio and microwave. A lot of the information that we receive, for example for the internet, is sent down optical fibre as either visible or infrared radiation. Infrared radiation, of course, heat radiation. So we use it in cooking, we use it in our remote controls. Now I have here an infrared camera which can pick up and give me a display of things which are hot and cold. The brighter the colour, the hotter the object. So for example, you should be able to see that my cup on the desk is hotter. You can even pick out the chocolate on the plate. As I get closer, you can see more clearly the heat from that cup, and you can even see my hand is much hotter than the surroundings. So hot, in fact, that if I leave my hand on the desk for a few seconds, you should be able to pick out my palm print next to that cup, a little warmer than the surroundings. Now, that is very useful when, for example, the police are trying to find someone in the dark, or a fire crew are trying to rescue someone in a smoke-filled building. The temperature difference between even the hot smoke and a human body enables them to find them when they would have no chance of seeing them visibly through the smoke. Then there's ultraviolet radiation. I've got here a UV lamp. It's quite low power, but at high power ultraviolet radiation can be quite dangerous. And we all know about using sun cream and staying out of the sun on a really hot day in the middle of the day, because the ultraviolet radiation can cause a sunburn, or it can even cause skin cancer. But this is quite low power. At these low powers, it's useful to sterilise water and prevent bacteria that are starting to form in it. Particularly useful in the developing world, where a plastic bottle, the kind we throw away every day, left in the sun for a few hours, will actually destroy the bacteria in a tainted water supply, so that it can become safe to drink. We also use ultraviolet radiation to check for forgeries. For example, in this £20 note, you should be able to see some speckles, which are areas of the paper that's been treated to show up under ultraviolet light. We can also use ultraviolet radiation to set fillings, and forensics teams can use ultraviolet radiation to look for biological material. For example, your wee will glow under an ultraviolet lamp due to the chemicals in it. So there are lots of uses for the electromagnetic spectrum. That's just a few, but hopefully it's given you a taste and you can try and find out some more. However, you've also got to be aware the electromagnetic spectrum becomes quite dangerous as you go to higher frequencies, higher energies. So even visible light can burn your eye if you're not careful. A very strong light source like a laser or the sun, for example. Infrared can burn. Microwaves, they can cause damage to the eye as well, but as long as we use low power ones or the correct units, so for example a microwave oven with the door closed is safe, our mobile phones are safe, but at high levels they can cause damage to the eye. And as I said earlier, X-rays and gamma rays at very high energies and very high frequencies can cause cancer. So we need to use the electromagnetic spectrum carefully, but if we do, the possibilities are enormous. Light
is only a small part of a wider electromagnetic spectrum, which can be considered to start with the visible colours: red, orange, yellow, green, blue, indigo, violet, although I never like to consider indigo. It's a shade that Sir Isaac Newton added to the list because he wanted 7 colours, 7 being a lucky number. But it's a dark blue or a purple, in the same way as we don't include brown or pink. Shouldn't really be there. But in the 1800s we discovered that there was energy beyond the red that we could see, a form of warmth which later came to be known as infrared or beneath red. Later we discovered that there are microwaves and radio waves beyond the infrared, and in the same way we discovered that beyond violet there is ultraviolet. Beyond that still, X-rays and gamma rays, some of which you're familiar with, some of which less so. However, the electromagnetic spectrum as a whole can be considered very much like light. Just like light, the waves travel at the same speed, they can travel through a vacuum, they're transverse, which means that they oscillate at right angles or perpendicular to the direction they're travelling in. They can be reflected, they can be refracted, they can be diffracted. But because they vary in wavelength and therefore frequency, they have a range of properties and we can make use of them in different ways. We need to be familiar with all of them, and we also need to be familiar with their uses and their dangers. And to summarise this, I often use the idea of a drawing pin. If we consider a drawing pin, nice and broad at the top, nice and pointy at the bottom, perfect for everyday use. Now if we add the different parts of the electromagnetic spectrum, if we put radio up here, then microwave, then infrared, the visible wavelengths come next, starting with red and working all the way down to violet. Then we have the ultraviolet waves, X-rays and gamma rays. And don't be confused, the fact that the last two are called rays, they're no different to any of the other waves except for their wavelength and their frequency. Back to this drawing pin. This helps us in two ways. One, at the top we have a nice long wavelength. Radio waves are the longest wavelengths in the electromagnetic spectrum. And at the bottom we have a short point, short wavelength. Now since they're all travelling at the same speed, that means that the long wavelength has a low frequency and it has a low energy. Short wavelengths down here for the gamma rays, they will have a high frequency and high energy. Now, the other great thing with this drawing pin is that it shows us the direction in which the danger comes with the electromagnetic spectrum. If you were to be prodded by a drawing pin, you'd like to be prodded at this end. It's the safe end. That low energy means that it's safer. Being prodded by the pointed end could hurt. That's more dangerous. And as a little extra, this end hurts more. Now since frequency is measured in hertz, slightly different spelling, we can consider that to mean more Hertz or higher frequency. Just might help you to remember it. The other thing you need to know about the electromagnetic spectrum is the generation, the uses, and how we receive each part of the electromagnetic spectrum. So, we'll lose the drawing pen. Hopefully it's served its purpose. We'll look at what creates, what records, and what we use each of these for. Radio waves, they're made by the sun, and they're received by an aerial. And they're used for information, be it TV or radio itself. We transfer energy using them. Microwaves, well, they can be made in a microwave oven or a mobile phone. Again, they can be received by them. And we use them as mobile phones. We also use them for heating. Infrared. Well, infrared is heat. So anything hot will make it. And you can record it with a thermometer. It's used for communications in optical fibres. It's also used for remote controls, but because it causes heating, we're now starting to see burns. So it's becoming dangerous. Visible light is generated by luminous objects. So again, we can look at the sun, we can record it with the eye, and we use it for illumination, we use it for photography. Ultraviolet is also generated by the sun, and you can detect it with a photographic plate. Don't get confused, you can't see ultraviolet. When people use ultraviolet paint, what you're seeing is ultraviolet light reacting with that paint and giving off visible light. It's the visible light that you can see. We use it for sterilisation of water, we use it in forensics, security, all sorts of things. But unfortunately, now we're into the region of skin cancer. Too much ultraviolet, too much burning in the sun, for example, can cause cancer. So, sun cream, well worth it. We look at X-rays. Well, I won't insult your intelligence by talking really about the uses. Again, they're generated by the sun, or we can generate them by causing electrons to accelerate and then slow down very rapidly. You can record them with a photographic plate. Or a CT scanner. They're used to see inside either the body or luggage, but again, overexposure can lead to cancer. Gamma rays, right at the end of the electromagnetic spectrum, again generated by radioactive isotopes, also by the sun, detected by a Geiger counter, that device that gives off a click every time radiation is detected. It's not always gamma radiation, but it often is. And they're used for radiotherapy, amongst other things. So actually for treating cancer. But we have to get the doses just right, because as we know, they can be incredibly dangerous. So that's the electromagnetic spectrum. Runs all the way from radio through microwave, infrared, visible, ultraviolet, X-rays, gamma rays. There is some overlap in some of the areas, but certainly long wavelengths at the top, short wavelengths at the bottom, Low energy, low frequency, relatively safe. High energy, high frequency, very dangerous.